Here's my project on orbital mechanics. So, the learning is my primary goal when it comes to this project. I wanted to better understand orbits and their relation to the concepts that we had learned in class. And then I wanted to present this information in a way that classmates who only had the knowledge from class could understand this new topic. And then I wanted to create a practice problem that required critical thinking and just knowing which equations to use rather than complex mathematics. So first, the introduction. So when it comes to reference frames, there were two reference frames that I learned about, inertial and non-inertial. The one that I focused mostly on was inertial, which means that there was constant velocity or no rotation. So using like a fixed star such as the sun, even though in reality that sun is orbiting the galaxy and other stars are orbiting the galaxies and it's all moving, using that as a reference frame, like the Earth is only rotating around the sun. So then I learned a few new equations. Most importantly, force between masses being force equals the gravitational concept, uh, the gravitational con, ugh, the gravitational constant times mass one and mass two, where mass one is greater than mass two, over the radius squared, or the distance between the two bodies squared. Next, we have the relative reference frame. So in this part, it's taking something such as the sun and acting as if it's not moving. So that way, only the Earth is moving around it. That way, the orbit is easier to calculate. So the equations are there on the left. Next is energy. So when it comes to orbital mechanics, energy is conserved, and the total energy is equal to kinetic plus potential. But the potential energy is gravitational potential, meaning it's due to the distance between two bodies. And using that total energy equation and understanding that energy is conserved, that means that while the bodies are closer together, there's a lesser potential energy, meaning there's a greater kinetic energy and therefore a greater speed. And the same is true when you're further away, the speed is lesser. And then those are the equations for gravitational potential energy and kinetic energy. Next is angular momentum. So spin angular momentum is referring to like the angular momentum of an object around its center of mass. Well, orbital, the one that is being fo that I focused on, or one that's more important to orbital mechanics, is that momentum measured around a center of rotation. So, like the momentum of Earth's rotation around the sun. So to change the orbital angular momentum, the forces is going to have to be perpendicular to r hat, which is the vector between the gravitational vector between the mass one and mass two. But since gravity is always going to be parallel to that vector, and gravity is the only force that is being felt, the angular momentum is constant. And then orbital equations, here are some equations there. What's most important is understanding terms such as apse line, periapsis, and on the next page, apoapsis. So the periapsis is that where the orbit is closest to the primary body, and apoapsis is inversely is the point where it's the opposite. So one important thing to note is eccentricity, which is the deviation of a curve from being circular. So if you go to the orbital equations continued, you can see that for circles, there it is perfectly circular, therefore E equals zero. For ellipses, it lies between zero and one. Parabolas, it's going to be one, and hyperbolas, it's going to be less than one. And then finally, escape velocity. This is something that I wanted to learn because it's very and finally escape velocity. So the and finally escape velocity is the necessary velocity needed for And finally, escape velocity is the necessary velocity needed to escape the gravitational pull of a mass such as the Earth. Well, finally, that led me to creating the class problem, which is shown below. And then here are my works cited.